Hello everyone. So this video is going to be me solving this problem about heat currents and also talking about the first law of thermodynamics and mainly the four processes of thermodynamic, the main four thermodynamic processes. So this problem is a problem that I encountered during round 2 of the Hong Kong selection test for the International Physics Olympiad. And round 2 is like pretty early, so the questions won't be really hard. And if you look at this problem, it's honestly like it's really not hard. So you can kind of see the difference between Physics Olympiad and Mathematics Olympiad. And AMC 12 is like a preliminary stage for Math Olympiad, and it's already like pretty difficult. And physics is, like it's not that difficult, although it could be still challenging. So basically, if you look at this problem, it's about heat currents, and one of the, actually I'll give you 5 seconds to decide if you want to pause the video and solve this problem or not. So I'm going to present my solutions right now. So the main kind of trick here for this problem is that you have to notice that the heat current remains the same throughout the three mediums because they're connected. So we have K1 D1, K2 D2, and K3 D3. And temperature is here. So the heat current is the same. And if we use the equation that I talked about last time, then we have this equation, and this equation. So how do we kind of eliminate the unwanted constants, for example, T1 and T2? Basically what we want to do is we want to take out the temperature like this. And this is the same thing. And we add them together. If we add them together, then the T1, T2 cancels out. So what we have is H is equals to A. I'm just going to fast forward this because it's honestly just meaningless mathematics computations. And so that's it. Basically, that's the heat current. And for B, we're supposed to find T1 and T2. And I'm not going to do this because, again, it's just algebra. You just substitute the heat current into the first two equations here. You substitute back into here. Not much else to do. And for C, you're supposed to find the equivalent conductivity. So basically, the equivalent conductivity is the heat equals to A K equivalent. And what is the equation? You're supposed to, it's defined in this way. And you basically equate the two equations. So you equate this with this. And at the end, if you equate these two, so A and TH minus TC cancels out. So what you have is the K equivalent is just D1 plus D2 plus D3 divided by D1K1 plus D2K2 plus D3K3. And basically that's it. It's really straightforward, I guess. So we return to this question, and let's start our journey to ideal gas. So basically, this is a PV diagram. A PV diagram is where you graph the pressure and volume of gas, and the temperature is basically, PV divided by NR using the ideal gas equation. And the higher the curve it is, the higher the temperature. And one thing I'll note about PV diagram is that when you have ideal gas, you expect the PV diagram to be just these curves. But however, when you look at here, it's completely different because there's a liquid vapor region. Like it's kind of like an interstate for the gas. So like this is obviously not ideal gas, and this is like, you know, the actual real gas. However, this is too difficult to compute, so we use ideal gas in, you know, the series, because usually competitions uses ideal gas. So yeah, not much to say about that. And now I'm just going to briefly introduce you the four thermodynamic processes. Let's start with isobaric. So isobaric, there are some properties of isobaric. Isobaric is basically where the pressure is constant. Isothermal is when the temperature is constant. Isometric is when the volume is constant. And adiabatic is when the heat is constant. And when the heat is constant, this is quite important. I'm going to talk about that later. So yeah, let's go on. And I'm also going to briefly talk about heat capacities. And heat capacity, this is molar heat capacity, by the way. And I think we talked about it a little bit in the last video. And this is CV basically means when the molar heat capacity when the volume is constant. CP is when the pressure is constant. And there's a very important kind of ratio, CP over CV. We're also going to talk about this later, and just remember this symbol. So yeah, now we're going to move on to the first law of thermodynamics. I would like to first note that the first law of thermodynamics is basically the conservation of energy. Why is it the conservation of energy, you may ask? If you look at the equation, this is the infinitesimal version. The general version is basically the internal change in energy is equals to the total input heat minus the work done by the system. The work done on the system will be negative work done. So just a note on that. And if you look at this equation, the heat itself is already a form of energy, and work done, of course, is energy. It basically means energy. So if the input heat is not equal to the work done by the system, it means there has to be an energy loss. So that's why we denote this as change in energy. How is this related to thermodynamic processes? Well, in Olympia problems, there are many many types of problems about this. For example, like when we're talking about work done by the system, how do we actually calculate the work done? You know, so basically, the work done is very interesting. It's basically when we talk about work done, we always talk about how we times the displacement with the force. And in this case, whoops, I switched to the wrong page. In this case, when we're talking about work done, let's say we're talking about gas, right? So there are some molecules moving around and stuff. And the pressure, where we have to relate this to pressure because we're drawing a PV diagram. Well, of course, we're going to relate to pressure. So the definition of pressure is basically the force times the area. And, you know, we can just express F as PA dx. And for P, so what happens here is we can actually separate the P out, and we look at A times dx. So what really is A times dx? A times dx is basically the volume, because, you know, there's a small volume change, a small x change, and then that's the area. And then if we times the area by the height or something, or the side length, we get the volume, the change in volume. So there you have it. If we integrate both sides, then we have the work done is equals to this. And this is basically the work done of a system, by a system. And if we look at the four processes, and if we actually go back, so isobaric process, obviously the pressure is constant and it has no relationship with the volume. So what can we actually do about that? We can just the integral doesn't mean anything. We can just take the P out and the V2 minus V1 because we're essentially finding the area down here. So yeah, that's isobaric. How about isothermal? So isothermal, we see that the temperature is constant. So what happens is, if we look at this integral, when the temperature is constant, it means that it's not related to anything. It's just constant. It's not related to the volume. So how do we relate temperature with, how do we relate temperature with pressure, right? So remember this equation, PV equals to nRT. And if we express P in terms of T and V, we get this. And we substitute back, we get this equation. And obviously we know T is constant, so we can take the T out. And N and R are just constants, and N is number of moles, R is like a constant. And we get this kind of famous integral, because we all know that this is the natural log. And basically that's the work done in an isothermal system. So yeah, isometric is basically when the pressure is changing, but the volume is completely, it just doesn't change. So there's no area. So the work done in this case is 0 for isometric. How about for adiabatic? Adiabatic is slightly trickier, and there's not much, like there's no clear way of establishing the work done. However, there's a very interesting property about adiabatic expansion. That's when basically the property is that the heat doesn't change. So if you look back to the infinitesimal definition, negative dW plus dQ, so no heat change. So du just equals to the change in work done. And if we know the internal energy, then we know the work done. So basically that's it. And so yeah, that's basically what we have. Also, we can use the first law of thermodynamics to deduce the other ones. Like for example, for isometric, the work done is 0. So the change in internal energy is equals to the heat. For isothermal, we can deduce this. We can sub this equation in back to negative dW, and we can deduce, if we know the heat, then we can deduce the internal energy. For isobaric, it's exactly the same thing. We know the work done, so we know we can deduce the third quantity using the second quantity. So yeah, that's the 4 processes. However, I would like to talk more about the adiabatic expansion or compression. So a very interesting property of adiabatic expansion is that when we write out the equation for the work done, as I said, du equals to negative dW, the change in energy is basically the change in energy is just N times Cv times dt. So remember, this is the molar heat capacity. The molar heat capacity is defined as the heat equals to the moles times the molar heat capacity times the dt. dt is basically the change in temperature, and here we write it as in the same way. And the dw is basically p dv, as we specified before. And sorry for the messy handwriting. And if we look at this equation, we can actually do what's called, I forgot what's called, separation of variables. Separation of variables is a very common type of skill that you use in integration. So basically what we want to do is, you see there's a dv here, you see a dt here. So we want to group the t and the v together, the t's and the v's together. However, we don't have any of those. So what we want to do, and we also have this unknown here, we have this thing, the pressure thing. So what we want to do is we want to express pressure in terms of v and t. So using the ideal gas law, we can group the wanted stuff together, and basically what we get is dt over t plus R divided by the molar heat capacity times dv over v. And what happens is, if you look at this equation, there's another property that I kind of forgot to talk about. It's basically how the molar heat capacity when pressure is constant is equals to Cv plus R. So basically, if you look at this equation, I'm just going to assume this is true first. I'm going to explain later. You can express R in terms of Cp minus Cv. So basically what we have here is whoops, wait. What you have here is Cp minus Cv divided by Cv. So we have Cp divided by Cv minus 1 dv over v. And remember, I talked about this before. This is sigma. Oh, I forgot what it's called. It's this constant thing. And if you look at this, if you integrate both sides, then what we have is ln t plus alpha minus 1 ln v equals to some constant. And using the log rules, we group these together. And basically, if we take the e out, this is essentially simplified to this. So this thing is always constant. So no matter what the temperature is, you can always find the volume, knowing what the heat capacity is. And similarly, because we know PV equals to nRT, we can similarly deduce that PV sigma is also equals to constant. So this is a very important, I would say, property of the adiabatic expansion. And I'll show you why when I'm presenting the solutions for what's called the Physics Olympiad on like a national-wide Chinese Physics Olympiad thing. And it's commonly used. So yeah, that's it for the adiabatic expansion. And next video, I'm going to talk about, wait, let me clear this mess first. Next video, I'm going to talk about entropy and the second law of thermodynamics. And this is in fact less talked about in Physics Olympiad because it's so hard, at least in preliminary stage. And so yeah, I'm just going to briefly talk through it because even myself, like I don't fully grasp the concept. So yeah, see you guys in the next video.